Now, to illustrate this idea of torque, we're going to solve a sample problem here. So here we have a horizontal lever. It's 3 meters long, extending from a pivot point, which is marked by this black X here. There's a 2 kilogram mass resting on the end, and gravity is going to pull downwards on the mass with its standard acceleration due to gravity of 9.8 meters per second squared. Now, given this situation, you're asked to do a couple things here. Number one, you'd like to find the torque or the net torque acting on the lever. In which direction will this torque cause the lever to rotate? And if you're provided with the moment of inertia, can you find the angular acceleration? Now, to do this, we're going to do a couple of things. First of all, we're going to find every torque that is present here. Every force will create a torque. So here we only have one force that pulls down on this object, and that's just the force of gravity, because it's going to spin the whole system around. So to do so, we can calculate the torque by either using a cross product or by using this magnitude style. And I'm going to be using the magnitude style because it's quite a bit faster. However, in order to do so, regardless of which method you choose, you need to find vector r. Vector r is always from the pivot point to where the force is applied. All right, so here vector r is effectively 3 meters to the right. Now, how you do this is up to you. How I would start is I would use my magnitude of torque equation here. Now, to do this, I need to know how big r and f are, and I need to have the angle in between them. Now, to find the angle in between them, you can just extend one of them outwards, and the angle you need is in between the extension and r. Or alternatively, you can line them up tail to tail. Now, if I take a look at this, theta is relatively easy to figure out. One is horizontal, one is vertical, so theta here is going to be 90 degrees. Now, to determine the other two quantities, I need the magnitude of r, and I need the magnitude of the force of gravity. So we'll start with r. The magnitude of r is just 3 meters, because magnitude doesn't care about direction. And we're told that in the problem. Now, with that being said, I need to find the magnitude of the force of gravity. Now, because I'm just looking at the magnitude, I don't need to worry about the direction. So I can just take the mass and multiply it by the magnitude of the acceleration due to gravity. Here my mass is 2 kilograms, and here the magnitude of my acceleration due to gravity is 9.8 meters per second squared. So all I really need to do is I just need to multiply these two things together. So these are in base SI units, so I will be left with a force that is in newtons. So we'll have 19.6 newtons. And lastly, as mentioned before, my angle here is 90 degrees. So to find the magnitude of my torque, I can do so by simply taking the magnitude of r, which is 3 meters, multiplying it by the magnitude of f, which is 19.6 newtons, and multiplying it by the sine of my angle. Now the sine of 90 degrees is just literally the number 1, so it's not really going to affect this. Now I can multiply these all together, and if I do so, I will get 58.8 newtons multiplied by meters. And although newtons multiplied by meters can give you joules, for torques it's customary just to leave them in newton meters, so as to not confuse the methodology that you're going to use. Now, with that being said, this is just the magnitude of my torque. So what I need to do is I need to look at this, I need to ask myself, well, is this going to make my system rotate clockwise or counterclockwise? And if you take a look at the system, the force is pulling down on the box. So my rotation is going to be in this direction, which is going to be indicated by my torque. So as a shortcut, right, you can put this into Cartesian notation if you want. Your torques will be in the z direction. But since we're trying to go clockwise here, this is telling us that our torque is going to be negative. So to write this in properly, I can go tau, tau is equal to negative 58.8 Newton meters. And again, this is me treating it as a vector, understanding that the negative sign indicates that the rotation is going to be clockwise. Now, this is just the torque from the mass. In order for me to find the angular acceleration, I need the net torque. However, there is only one torque present here. Right? There's no other forces here except for that created by the mass that is resting at the end. The reason you know this is if there were to be another force, I would have to provide you with additional masses, such as the mass of the lever. So here, my net torque just consists of adding all the different torques together. And because there's only one, all I need to do is write it down. So right here, we have the net torque. So we're done this one. Since our net torque is negative, it's going to indicate the direction that we're rotating in. So this will be clockwise. And lastly, we can actually find this angular acceleration. To do so, we're going to use this final equation here. I know that the net torque is negative 58.8 Newton meters. And for the moment of inertia, I've been told that it's 12 kilograms meters squared. And thus, all I need to do here is solve for alpha. So putting this all together, alpha is again a vector quantity. We're going to use the exact same sign convention, but alpha will be 4.9 seconds to the negative 2, or 4.9 hertz squared, however you want to write it, but it will be negative. And what this tells us is alpha here is, again, clockwise, because it should reflect the net torque. So what you'll notice here is the process is almost identical to what you would be dealing with when you're dealing with forces. You can calculate a torque. It does require additional information, such as the force, the vector from your pivot point or axis of rotation to where the force is applied, which involves both their sizes and the angle between them. You do need to assign a direction to your torques because it is a vector quantity. The easiest way to do this, though, is to have positive things be counterclockwise and negative things be clockwise. As with our force-like systems, there is a net torque, which is always just equal to the addition of all the individual torques. And this net torque is always related to a mass-like quantity, in this case the moment of inertia I, multiplied by the angular acceleration that you see. So in terms of problem solving, the torques are different, but the problem solving steps are exactly the same as they were when you're dealing with forces. And that should be no surprise because these torques are basically the rotational equivalent of a force due to the fact that our forces are being applied away from where our object is going to rotate around.